In this video and on this page, we're going to practice using the derivative rules that we established in our last section, along with the simple derivative properties that I gave in the section above this video. So let's suppose I wanted to evaluate this indefinite integral. I have the indefinite integral of 16 e to the t power dt. So I'm integrating in this case with respect to t, which means I'm just thinking about t as my variable rather than, say, x. So in this problem, I might look at this part in particular, and I might say, hey, e to the t, that looks a lot like e to the x. So I think I would understand how to integrate this problem if it was just e to the t dt, because we gave that derivative formula last time. But it might be worrying to you that we have this 16 in front. That's kind of perhaps a problem, or perhaps maybe we don't know how to deal with that yet. But luckily for us, we gave two properties of indefinite integrals, and one of them said, hey, if you have a constant multiple, which in this case 16 is a constant multiple, you can factor that out to the front of your integral. So I can rewrite this as 16 times the integral of e to the t power dt. So all I did was take this 16 and factor that to the front of my integral. And what that means is that I can sort of ignore that 16 exists. I can just say, well, now I just need to focus on integrating this e to the t power dt. That's all I need to be thinking about here. So at this point, hopefully this looks pretty familiar. I say, well, e to the t dt, that looks a lot like e to the x dx. And we said e to the x was, again, its own antiderivative. The antiderivative of e to the x is just e to the x, and then, of course, plus our constant of integration c. The only difference this time is here we have a different variable t, but it's going to follow the same exact pattern. So my antiderivative for this part right here is going to be e to the t power plus c. Now, I don't totally get to ignore this 16. I don't just get to say, well, let's ignore it. It's not going to be a part of my answer. It does have to carry down, which means I'm going to multiply my antiderivative by that 16. So I'll have 16 times e to the t power plus c. So there is my first antiderivative. I think factoring out constant multiples, it's not necessary in every single problem, but it can be helpful if you have a more complicated integral and you want to simplify it a little bit more so that you don't have to think about as much and you don't have to juggle too much in your brain. But if it's a step that you want to skip, in most problems, I think you can get away with it. We'll look at one more example here. In part B, I have the indefinite integral. We're going to be integrating 2x to the fifth minus 3x squared plus 1 dx. So we're integrating with respect to x here. That's our variable. And in this case, the big thing that's different is that we have these minus and plus symbols here. We're integrating more than one single term, which might be worrying or it might be concerning to you. But one of those integral properties that I gave right above this video said, hey, you know what? You can take an indefinite integral and you can distribute it across addition and subtraction. So I could take this one integral and I could break this up into the integral of 2x to the fifth dx minus the integral of 3x squared dx plus the integral of 1 dx. Now, you don't necessarily need to show this step, but this is actually what's happening behind the scenes. So then I've just taken this one big integral and broken it up into 3 smaller integrals, and at this point, I should be able to use my power rule here. So that means, remember, we need to add 1 to the power. So we add 1 and then divide by the new power. Those were our 2 steps. So here, when I integrate 2x to the 5th, I'm going to add 1 to the power, 2x raised to the 6th power, and then divide by that new power of 6. Minus, for the second term over here, I'm going to add 1 to the power, 3x to the 3rd power, divided by my new power of 3, plus, this one is perhaps a little bit tricky. How do I integrate a constant? Well, 1, I can actually rewrite this as 1x to the 0 power dx, because I know that anything to the 0 power is 1. This really says the integral of 1 times 1 dx, which is exactly what we have down here. So when we're starting off, it might be helpful to think about that as 1x to the 0 power, because now it's a lot easier to apply our power rule and see, okay, we're going to add 1 to our power. 0 plus 1, this would be 1x raised to the 1st power, and then divide by our new power. Our new power was 1. At this point, we found our antiderivative, which means we need to add our constant of integration. We can't forget about that. So we're going to add on our constant of integration plus c. From here on out, all I am going to do with the rest of this problem is then just simplify this. So I'm going to simplify that first term. These are both divisible by 2, so this would be 1 and 3. So this would be 1x to the 6th, or just x to the 6th power, divided by 3. Minus, in that second term, I can cancel my 3's, so we can just say minus x cubed. 1 times x to the first would just be x, divided by 1 is still just x. So we can say x, or we can say x to the first power, and then plus our constant of integration c. So there is our solution to this antiderivative. Now, like I said, you don't necessarily need to break this integral up into 3 separate integrals. I don't need to see that in your work every single time. I expect as we get more comfortable with antiderivatives and as we practice more and more and more of these problems, you will start to feel more comfortable jumping down to this step here, or perhaps even just to that final boxed-in answer. If you are feeling confident enough with your integration and just want to jump straight down to that final answer, I think in this particular case, that would be fine. There's not really much work to show here. We're just going to do some addition and dividing here. So these properties you don't necessarily need to show every single time, but I do think it can be helpful when we're looking at new or potentially complicated indefinite integrals, because integration is a process that can actually get really complicated really, really fast.